Third, 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 third.
Okay. Good evening, all of you.
Good evening, sir.
So let us start today's lecture. So I just share the slides. Okay. So these are the things we were discussing in the last class regarding this. Yeah, why we prefer to transmit AC rather than DC for power transmission. And in the last class, we have already explained that in case of DC, that if you are sending the voltage or the power to some remote load, then there will be some drop due to the resistance due to the conductor, and that will also give you some power loss. So that is actually the power loss due to the ohmic resistance. This is called ohmic drop. Okay, I square R is your power loss. Okay, and then we have seen that in order to reduce this power loss in the transmission line, what we can do, we can increase this VL. If we increase the VL, that is the voltage across the load, then we can reduce this power loss. Okay. However, in order to increase this VL, I have to increase my V. Okay. The input voltage should be increased. Then only you can have your VL large, because VL is equal to V minus IR. Okay. So you, in order to increase VL, you have to increase your V, and since you are increasing your V, you need to increase your V. That means you have to do a high voltage transmission. Okay, now this high voltage transmission, as I said, it may be dangerous. Means when you are having the load at your home for domestic application, this high voltage will be dangerous. So we will require to step down the voltage. Will require to transmit the current, the power at a high voltage, but the voltage has to be stepped down at your home. Okay, when you are connecting your load at your home, then it needs to be stepped down. Now first, that can be done only in case of AC using an ideal transformer. Means using a transformer. Okay, ideal transformer will have no power loss, so it will be basically transmit the power from one side to the other side without any loss in the transformer. Otherwise, there may be some loss. Generally, practically, there is some loss in the transformer. Otherwise, more or less the same power is transmitted. So what we do, we make this V1 very large. Accordingly, the power which you require at this end, PL, that is that comes here at the, this is called the primary side of the transformer. This is called the primary side. That power PL appears at this end of the primary side of the transformer, where PL will be equal to V1 into I1. Since V1 is large, then I1 will be small, and hence the power loss in this primary side, that is the long distance transmission, the power loss will be small. Okay. Now the same power PL which appears on this side, that is transmitted on the other side, secondary side of the transformer. Okay, so here you are having PL is the power, and the voltage that appears here is equal to V2, which is stepped down. Okay, the step down ratio of the voltage, that depends on the turns ratio. How many turns? You can see I have shown it like a coil. So you'll be having some coils on the primary side, some coils on the secondary side. So depending on the number of turns in the coil, okay, you will be having your V1 is to V2. It will be in the ratio of the number of turns on both the sides. Okay, so generally this secondary side will be having a very small number of turns compared to the primary side. So V2 will be stepped down in this case. If you require step up, then you have to do the other way. Okay, in step down, this side the number of turns will be small. Okay, so your V2 will be small, but I2 will be now large, because it is again equal to, it should be equal to your power delivered here. V2 I2 should be equal to PL. I2 is large, but since this is a local circuit, it is just a circuit there in your locality. So this conductors here, they will be of smaller length, and hence they will not offer much power loss. The power loss will be small compared to the power loss in the long distance transmission of the power. Okay, so that is how in AC we can take care of this high power voltage transmission, but stepping it down in the locality. There, for example, I have shown that generally from the grid station, when the voltage comes to our locality, it comes at a voltage of 11 kV. Okay, whereas at home we have it as 220 volts. So you can find out the 11 kilo is to 220. This will be the number of turns in the primary side and the secondary side. This type of transformers you might have seen that in your neighborhood there will be somewhere on the roadside. You might have seen the transformers where this step down of the voltage takes place. Okay, 11 kV to 220 volt, something like that. Okay, so that is about the power transmission. So when we do power transmission, we don't go for DC. Okay, however, in DC there is one advantage. In DC, the advantage is that the L and C, the inductance and the capacitance in the line, transmission line, will be having no effect. Okay, that is there. Okay, however, since we have to also reduce the power loss, we will not go for DC. Okay, we'll go for AC. Now this AC will have some, this L and C will have some effect in AC, but for power transmission we generally keep the frequency very small, 50 hertz in our country and in some other countries, and in some countries they have 60 hertz, only 60 hertz. So it is a very small frequency. So L and C in power line transmission you don't have much effect because your frequency is very small. Okay. Now the question comes, when I am doing electromagnetic wave transmission over the transmission line. As I said, why I need to do it? Because I said that, okay, EM wave we have studied, that EM wave can be transmitted in air wirelessly. Okay, but when I transmit EM wave wirelessly in the air, I cannot make it guided. That means I cannot transmit it from one point to another specific point. I have to basically broadcast it in the air, and then my receiver has to pick it up from the air. Okay, I cannot make a guided, means I cannot specify that the EM wave will only go from one point to another point. Okay, I have to just radiate it all around, and then my receiver has to pick it up. Okay, so for guided transmission, where it is required that no one else should be interfered with my signal, the signal will only go from one point to another point without being radiated in the air, then I have to use some guided medium. You can understand it, that I have to use some guided medium, otherwise it will just radiate all around. Okay, in the wireless means it has to be radiated all around. Okay, and in that case, some another problem is there when I am doing it, radiating it all around. unnecessarily if it is not required. If it is just point-to-point transmission, then unnecessarily I am radiating it all around, means I am doing power loss. Power is radiated on all around, but my receiver is located only at one point in the whole world. It is located only at one point, but I am just sending it all around. Unnecessarily, I am wasting power. Okay, so in that type of situation, I will require only point-to-point transmission. Another case may be where I need secured transmission. I don't want anyone else to tap my signal. Okay, my signal is, it should go in a secured line. Then in that case also I will require some guided medium like this. Okay, so in that case I have already said that there are two ways. Either I will be using the transmission line or I will be using waveguide. Okay, waveguide I will come afterwards. Now when talking about transmission line, we are now finding that the transmission line is having some L and C, which we have already studied. That transmission line can be modeled where there will be some L and some C. L will be responsible for the voltage drop along the line. C will be responsible for leakage of current in a parallel path. Okay, in a parallel path, leakage of current, C will be responsible for that. Accordingly, when the signal is getting transmitted over the transmission line, the voltage and the current both will keep on dropping, attenuating with length. As it goes along the conductor, it will keep on reducing voltage and current. And voltage and current reducing means my power is also reducing. Okay, that is the problem. And that we have seen that what is the impedance offered by L, which causes the voltage drop. The impedance is omega L. Omega is your frequency, 2 pi f. Omega is equal to 2 pi into f is equal to frequency. So when frequency is more, your impedance due to inductance is more. Okay, so more voltage drop will take place. When omega is more, your admittance due to capacitance, omega C, that will be more, so more leakage will take place. Okay, so that is the problem. Okay, so you see that advantage, as I have written here, advantage of DC circuit is L and C do not come into play. Okay, so but in AC circuit we have to bear the effect of L and C, which we have seen earlier. L and C are responsible for two things in my circuit, that is phase shift and attenuation. Phase shift, I have already said that R plus j omega L into G plus j omega C is equal to, I can write it as gamma square, where gamma can be written as alpha plus j beta. Alpha is my attenuation constant, beta is my phase constant. So beta gives you the amount of phase shift per length. Alpha gives you the amount of attenuation per length. Okay, so you can see here that the effect of L and C is over phase shift and attenuation. Okay, these two things will take place. Okay, now let us see some special conditions. In special conditions, what happened for DC? Okay, for DC, that means if omega is equal to 0 or mute your mic. If omega is equal to 0 or both L and C equal to 0. So either if it is DC, in case of DC, although in obviously in electromagnetic wave transmission we don't have DC case. Okay, it is just for the sake of writing I have written it here. In case of electromagnetic wave propagation, but as a special case I am considering L and C equal to 0, although practically you will be not having that, but suppose L and C is equal to 0, then you see your alpha turns out to be equal to 0. Okay, you can just check here, because then your real part will be 0 in this case. Okay, if L and C is equal to 0, then you will be having alpha is equal to 0. Okay, So alpha is equal to 0 means that you will be having, so alpha is equal to 0 means you will be having your no attenuation. So that means their signal amplitude will, sorry, I'm saying beta is equal to 0, not alpha is equal to 0. The imaginary part will be 0. Here you can see the imaginary part is becoming 0. So gamma is equal to Rg. That means alpha will be equal to plus minus root over Rg. Okay. So there is alpha, but beta will be equal to 0. You can check it. Okay. So in this case, signal will be decaying exponentially, but there will be no phase shift along the length. Okay, there is no phase shift along the length. So in this case, you will be having this alpha only will be giving you the attenuation. So your signal will be actually, it will be not in the form of a waveform that I have shown it in some diagram. Just a minute. Okay, this one. This waveform is due to the phase shift. Okay, so in that case, you will be not having this type of waveform, but your signal amplitude will just exponentially keep on decaying. It will exponentially keep on decaying. So if I sketch the waveform, it will be not in this form, but it will be like an exponential curve. Okay, so that will be the case. Okay, when your beta is equal to 0, alpha is equal to plus minus root over R. So it will be only decaying, only attenuation. If R and G both equal to 0, okay, in that case you will be having alpha equal to 0. So this is a special case again. I am taking that R and G both equal to 0, then your alpha is equal to 0 and beta will be equal to omega into root over LC. So in this case, there will be no attenuation but only phase shift. Okay. So again, this waveform will in that case look like waveform with constant amplitude. Okay. So the waveform in that case will become constant.
Excuse me, sir.
How
R and G can be simultaneously 0?
Why? G is having nothing to do with it. This is just I'll show you. G is not the same one, na? G is in the parallel part. Yes, you can see here. See, this is my G. This is my R.
Okay, sir.
Okay, so G0 means G conductance 0 means it is open circuit. Okay, G0 means this is open circuit,
Okay,
and
sir.
R0 means this is short circuit. Got it? So R is your blue resistor, and G is your this resistor. Okay. Okay. So this,
Yes,
so don't mix up with R and G. This G is the parallel conductor. Okay, the conductor coming in shunt. Okay, R is in the series. Okay. Okay. So it is
yes,
not
sir.
that this G is just the reciprocal. Then RG will become 1. Okay, it's not so. Okay. So it is not that these R and these G are related. They are different. Okay. Clear? Okay. So if R and G both equal to 0, that means there is no leakage in the shunt, leakage of current in the shunt path, and there is no voltage drop in the series path. Then in that case, alpha will be equal to 0. Obviously, there is no attenuation because no current is leaking, no voltage drop is taking place. So your waveform will be there because beta is there. So phase shift will take place. So waveform will come. Okay, it will, the EM will have some wave type of, if I sketch the waveform and sketch the propagation of the waveform, it will be like that, what I have shown here. This waveform will be there, but the amplitude will remain constant in that case. Okay, the amplitude remaining constant. So these are two special cases. Otherwise, alpha can be calculated. It is equal to this. Okay, from here you can do it. Okay, and beta will come out to be equal to this. Okay, this is the alpha and beta. Now you see here in this expression, omega is coming into picture. So for appreciable values of R, G, L and C. So here I have taken two special cases. In one case I have taken L and C equal to 0. In other case I have taken R and G equal to 0. Otherwise, if L and C are not equal to 0, R and G not equal to 0, so whenever R, G, L and C will be there, okay, both alpha and beta will, some values will come, and there you will see that this omega is coming into picture, okay, because omega you can see that it is getting multiplied inside, so omega will have some effect, okay, on alpha and beta. So that is what we were talking about. So omega is creating some problem. So that's why this transmission line cannot be used for very high frequency transmission. To some extent, to up to some frequency, you can keep on using the transmission line. There will be some attenuation, there will be some phase shift, and all these things will be there. Okay, but that is okay. Up to till some frequency it is okay. But when this omega is very, very large, then there will be problem. The attenuation may be so high that your wave will not go to far up distance at all. Okay, it will just die out. Okay, so very high frequency cannot be transmitted over a transmission line. Again, in this page I have given some calculation, just approximate calculation of gamma. Okay, this gamma I have calculated from here. Okay, from this gamma has been approximate calculation using the Taylor series and all these things. You can just check it. Okay, this is how I have done it. So assuming R and G very small, okay, so they are very small, so their product is, I am taking that RG tends to 0, and accordingly I have made some approximation here. Okay, and then this is the Taylor series expansion. I am taking that root over 1 plus x is approximately equal to 1 plus half x. If we take that, then your alpha will come out to be something like this. Okay, beta will come out to be something like this. So this is approximately, you can see that alpha will be more or less independent of frequency. Okay, and beta will be it will be having this will be approximately equal to omega into root over LC, which we have found it here. Okay, this is the case, because here we are taking not exactly R equal to 0, B, G equal to 0, but we have taken them very small. So if they are taken to be very small, there will be some attenuation, but again in this case it is more or less alpha will be independent of frequency. This is again just an approximate calculation. Okay, so this is about that question. Someone asked why do we don't use DC and all these things. So we don't use DC transmission and all these things because of this reason, and how omega is coming into picture when we are transmitting the radio waves over a transmission. This is something, means you need not to memorize all these equations right now, because these things you will be studying it later on. It is just for your knowledge I have put all these things. Okay, you can read it, but you need not to memorize the things. It will be not asked in your question. All these mathematical things will be not asked. Okay, very simple thing will be asked. Okay, next someone asked me about the velocity. Someone raised the question that why I have written C. Okay, why I have written that the velocity of the radio wave in the transmission line, I said that it will be approximately equal to C. Okay, actually it will be not equal to C, that is true. It will be approximately equal to C, but again that will be only in a certain case. Okay, so let us see that. Okay, when it will be approximately equal to C. Okay, let us see that. Okay, let us assume the case again when it will be equal to C. That first assumption will be that if R is equal to 0, G is equal to 0. That is the assumption. So suppose that is the case, then beta is equal to omega into root over LC. That we have already seen. And what is beta? Beta is equal to 2 pi by lambda, because beta is the phase constant. It gives you the phase change. per length. So in lambda is the wavelength. So in one wavelength, you will be having 2 pi phase change. Okay, 2 pi phase change. So that means beta will be equal to 2 pi by lambda, which again is equal to omega into root over LC. And you know what is V? Velocity will be equal to F into lambda. Hence, putting omega is equal to 2 pi F and all these things, you can see that basically it comes that V is equal to 1 by root LC. So 1 by root LC is your actual velocity that will come if you do the calculation taking R equal to 0, G equal to. So if you in your transmission line, if R is assumed to be equal to 0, G is equal to 0, if these two assumptions are taken, then your velocity will come out to be equal to 1 by root over LC. So now we have to find out what is L and C for that conductor. Now first let us take this L case, calculation of L. This is one conductor. I am taking this parallel transmission line. So this, I am taking a cross section of the transmission line. So this is the cross section of one conductor. This is the cross section of another conductor. Okay, and I am assuming that both the conductors are of same radius, okay, R, and they are separated by a distance of D. Okay, then the inductance offered. Okay, this will be the inductance due to the magnetic field created when the current is flowing through the conductor. There will be some flux linkage, okay, because of the magnetic field created around. And accordingly, I think this you have studied, this derivation you have studied in your CBSE class 12, or maybe in other boards also. At least I know in CBSE you do this. Okay, so when current is flowing through a conductor, the inductance due to that flow of current in that conductor, in that case, the inductance per conductor per length, it will be per length actually. I have already given the unit in Henry per meter. So per length inductance offered by each of these two conductors is equal to mu by 2 pi log of capital D by small r. This derivation you must have done. Okay, if not, you can look back into your class 12 book. Okay, so what is the total inductance then? This is the inductance per conductor. So the total inductance that will be offered by these two conductors, okay, that will be the sum of these two. Okay, it will be the sum of these two, and that will come out to be, if we can check that, it will come out to be mu by pi log D by R. Okay, and mu you have, you know what is the value of mu, that I have already given you earlier. So if you put the value of mu, okay, for this case, okay, this mu actually, if I take this mu for the case of free space, okay, I am considering again, that is another assumption we are considering, that this is in free space. Okay, if we take this in free space, then it will come out to be this. Okay, anyway, so otherwise L is equal to this. This is the expression, and for free space it will come out to be this. Similarly, now you have to find out the capacitance between the two conductors, and if we can, again, this one also you have studied earlier, the capacitance between two cylinders, okay, two cylindrical shaped conductors. If you must have done that derivation also. Okay, so that comes out to be this. The capacitance between two conductors, the capacitance between these two conductors will come out to be this. Again, this derivation you can look back. So what is your V now? I put these two expressions. You just multiply L and C, and if you take if you do all this cancellation and all these things, it will come out with V will be equal to 1 by root over mu epsilon. Okay. However, this mu is the mu of the permittivity of the medium around the conductor. This epsilon is also the epsilon is the permittivity of the medium surrounding the conductor. Mu is the permeability of the medium surrounding the conductor. Okay. Now if we assume, okay, again, so that is the case actually why I have taken V approximately equal to C. So if we now assume that this is in air, no dielectric or anything is there in between the conductor. So if the transmission line is just in the air, and in most cases, we consider that mu and epsilon of the air is somewhat equal to the free space. Okay. So mu is approximately for air medium, mu is taken to be approximately equal to mu naught. Epsilon is taken to be approximately equal to epsilon naught. Although not exactly equal, but more or less we can consider. Okay. So in that case, this V turns out to be equal to C. Okay. So you can see, so under certain conditions, we can assume that if the transmission line is in the air medium, then we can take that the velocity is approximately equal to the velocity of the light. Okay. So that is what actually I have taken. But if it is given that the medium is different and all these things, then obviously your velocity will be different. Okay. In that case, you have to calculate the velocity using this. Okay. One thing, somewhere sometime back in this notes itself, I have given that unit of 1 by root over LC. That time I have said that this is equal to hertz. Okay. So root over LC, I said that it is equal to second unit. Okay. So just don't get confused with that. That's why I have mentioned it here. Somewhere I have written it. Let me check that. This one actually, I have written it specifically somewhere. Not this page. Here. Here you see the unit of root over LC is second. L is in Henry, C is in Farad. Okay. And hence the unit of frequency F will come out to be 1 by second, that is hertz. Okay. So here don't get confused. Here L is the inductance. Okay. Full inductance of my circuit. Okay. In this circuit, I have taken a circuit. Huh? So in that circuit, this is the circuit. So this is the L. Okay. Total inductance of this inductor. C is the total capacitance of this capacitor. So it is in Henry and Farad. Okay. Whereas here, okay, don't get confused in this case. Here this L is inductance per meter per length. C is the capacitance per length. Okay. So their units are actually Henry per meter, Farad per meter. So you see this VT, so this one turns out to be LC turns out to be root over LC turns out to be second by meter root over LC, because here you have by per meter. So it turns out to be second per meter. That will be the unit of this, and hence unit of V is meter per second. Okay, so that's why here it is V. Okay, so don't get confused. That L and this L is defined. That L is the total inductance. Here is the inductance per length. Similarly, there the C is the total capacitance, but here the C is capacitance per meter. That's why here it comes out to be meter per second. Meter per second. It will come out to be. Okay. So that's all about, I think, voltage source and all these things we have discussed already. So that's all about this explanatory notes. So today I'll just continue with the few more slides after transmission line, and that is the waveguide. And so that next class we can start with the other things. Okay. So this is the other type of guided transmission medium. Okay. One is the transmission line. So guided means my electromagnetic wave will be transmitted over a particular medium, it will not radiate all around. Okay, you will be confining the electromagnetic wave, the radio wave, to flow only in a through a particular medium. Okay, so the one we have already studied, that is the transmission line. And the problem with transmission line is that high frequency transmission is not possible. Okay, there are, as we have discussed, it gives some problem. Okay, so a better guided medium which can support high frequency transmission, in fact it can support microwave range frequency, which is very, very high, and in fact it is used for microwave transmission, that is the waveguide. Okay, so when you will be studying your microwave I think in third year you will be studying it, so that time in the lab you will be using it. This waveguides you will be using in the lab. You will be connecting your all the microwave devices, you will be connecting it using waveguides. Okay, so waveguides is the only medium. There you cannot connect the microwave devices using simple transmission line, because simple transmission line will not allow the microwave radio waves to flow at all. It will attenuate the whole thing. Okay, so there you will be connecting them using the waveguides. You will see the waveguides that time. Okay, you will use it in the lab. Hopefully by that time this pandemic will be over and you will be having physical laboratory that time. Okay, so anyway, just some basic idea about waveguide. What is waveguide? So it is a structure which can guide or transport EM wave, okay, with minimal loss. So that was the problem with transmission line. Okay, we have seen that there is some attenuation and hence there will be power loss. Okay, there are two types of waveguides. One is the metallic waveguide, which is used in high frequency microwaves, millimeter waves. Okay, and generally there are two types of metallic waveguides. The one is the hollow rectangular type, and the other one is the hollow circular type. Okay, there are two types. Mostly you will see in practice we use rectangular one. Okay, in the labs mostly you will see rectangular ones. Okay, the other one is the dielectric waveguide. So it's not hollow. The first one is metallic. The outside boundary is made up of metals. Inside it is hollow. But the dielectric is not a hollow one. It is basically made up of some dielectric medium, dielectric material, which is there inside. One example, very common example, is the fiber optic. Okay, optical fibers are used nowadays, you know. Okay, mostly it is used for transmission of this digital signal in the LAN. Okay, in your local area, for example, in our IIT campus, the LAN network, all the departments, hostels, and all these are connected using this fiber optics. Okay, so this is the other type of waveguide. Okay, metallic waveguide is actually problem is it is not that flexible. You can understand it is made up of metal, so you cannot bend it that much. Okay, whereas this dielectric waveguide, as you know, you have seen optical fibers, they can be, you can twist them. So that is the advantage of this. It is very flexible. Okay. Parallel waveguide is basically formed by two infinite parallel conducting planes. Infinite, I am saying, okay, means we are considering that infinitely extended conducting planes. Okay. Whenever there is, you have some abrupt ending of this waveguide, there will be some reflection and all these things. Some reflection takes place and all these things. So otherwise, we just assume that okay, it is infinitely extended, so there is no reflection or anything when the electromagnetic wave is flowing through. Okay, and this energy is, it flows through this in between these two parallel plates. It will be the EM wave will be flowing through it. Okay, how? Let us see. Just from the diagram, we are not going into details. Okay, that again you will be studying it in your microwave engineering. Just an idea that the electromagnetic waves will be between these parallel plates. Okay, there are three types of uh, transmission. Okay, one is the transverse electric field, the other one is the transverse magnetic field, and one is the transverse both electric and magnetic. Pictorially, just see how it happens. This is the TE mode. Okay, so the electric field is in the direction perpendicular to the flow of the wave. Wave will be flowing like this. Okay, wave will be flowing in this direction. Electric wave is in this direction. So electric field is parallel to it. How is the magnetic field? Because magnet, you know that electric field, magnetic field, and the direction of propagation, they should, all these three should be perpendicular to each other. So here you can see the magnetic field is actually in this direction. Okay, this one actually is there. Magnetic field actually is in circular, but this one actually will have no effect because it comes parallel to the direction. So this one, which is in the transverse direction, that actually have the effect which results in the flow of the wave. Okay, so you can see how the magnetic field is created, how the electric field is created, and because there is a magnetic field component which is perpendicular to the electric field, you will be having the wave propagating in this direction. Okay, so this is how the wave propagation takes place. The TM mode is just, you can see here how the electric field is here and how the magnetic field is here. So here the magnetic field will be in this fashion. Okay, so the magnetic field is basically this component of the magnetic field. This component of the magnetic field is in between the two parallel plates, the upper plate and the lower plate. Okay, and the wave is propagating in this direction. Okay, so this is how the TE mode and TM mode. We are not going into much details because these things you have to study all the derivations and all these things. You'll be studying it afterwards. Okay, just a basic idea. And this is how the transverse EM mode. Okay, you have the electric field between the two parallel plates. You have the magnetic field like this. Okay, so it is in this direction circularly. Okay, so you have the electric field, you have the magnetic field perpendicular to each other, and your wave will be propagating in this direction. Okay, so this is how the TE mode transmission takes place. Okay, so magnetic field, basically it is the, you can see it is basically this electric field like this and the magnetic field like this. These two are combined together and that gives you this. Okay, the electric field and the magnetic field are basically combined together. Okay, so these are the three modes of transmission in a waveguide. Okay, and next, just the last slide here on this, that optical fibers. So again, just a basic idea on optical fibers is that you have, this is the structure actually. You have an outer plastic jacket, then you'll be having a glass cladding, okay, and inside you have a glass core. So here you have a glass dielectric through which the light, so light is the electromagnetic wave which flows through this, okay, flows through this medium. Okay, how? The principle used here is the total internal reflection. Okay, so this one, you can see that if the direction of light, okay, if the direction of a ray is like this, means it is below the critical angle, you know that the incident angle, if it is greater than or at least equal to the critical angle, then you will be having total internal reflection. Okay, so whenever the incident angle is less than the critical angle, okay, less than the critical angle, then this ray will pass through this glass cladding. Okay, it will pass through the glass cladding and will get absorbed in the outer jacket. So that is a loss. That will be lost. This part of the ray will be lost. Whereas if the light is incident on the glass cladding at an angle more than the critical angle, then there will be total internal reflection like this. Total internal reflection like this. and it will keep on going along the fiber. It will keep on moving. Okay. So that's why in fiber optic, when we are transmitting at the transmitting end, the light has to be incident at a particular angle. Okay. So you have the device. Obviously, there are some devices and all these things. They are doing the business. And to make your light very, very pinpointed, okay, very narrow beam of light, because then only otherwise the light will be diverging in all, some part of the light will get absorbed in the cladding. So to make your beam very, very narrow and pinpointed with an angle greater than the critical angle, we use the laser beam. For transmission of light in the optical fiber optics, we use laser beam. Okay, and in fact, this is the band of the light. Near infrared part of the spectrum is used, where we have this 850 nanometer, 1300 nanometer, and 1550 nanometer. These are the wavelengths. These are the wavelengths of the light that is used for transmission. They can form a very narrow beam. Okay. So I think that's all about the fiber optics. It's again just a basic idea. Okay. And for transmission, I have just written one point. Photodiode and photodetectors are the two transducers used at the two ends. Okay. Photodiode, depending on the amount of electrical energy it will generate, photodiode will generate some actually for not sorry, it should be LED, okay, light emitting diode, okay, not photodiode. Light emitting diode will be there, laser beam producing the laser beam, producing the light of this range, and then on the other side you will be having photodetectors, okay, for detecting the received signal. Okay. So till this for today. Okay, so next class we will start with something new. Okay, something means we will just proceed further with this. Okay, so if you have any question right now, you can ask me. Any question? Okay, I think you are not having any question. Then you can start leaving. Okay, you can leave.
Thank you, sir.
Okay, bye.
Thank
See
you,
you
sir.
on
Thank you, sir.
Friday. Okay.
Thank you so much.